Thanks for staying so long, and thank you for the organizer to have me here to have a chance to talk about our recent research. So I'm very glad that the last two speakers are talking a lot about 2D. Talking a lot about the 2D spectrum. So this basically this, and we're doing theory to try to calculate it. And this is our system, very similar to Jeff's talk. So we have some excitons here, and then however we are in a 1D system. So this is basically my topic, and I'm Jia Wang from Swinburne, and I'm working with Hui and Shaji together for this project. So there are a lot of terms here, so let me break it down a little bit. So exciton, we already hear about exciton a lot in this conference in general, and particularly in this section. So basically, exciton is basically a balance state of an electron and hole pairs. So because we all know that electron and hole can annihilate, so they are naturally strongly coupling to light, and hence that's why it's very useful in this kind of light harvesting technology we can hear about in this conference and also the webinar about a month ago. Another very interesting material that Jeff just mentioned about in his talk is that the monolayer TMD. In there, this is also a very good platform to study excitons. The reason is because in this kind of materials, that exciton is actually tightly bound, and they have a lot of potential applications. For example, in optical electronics. However, you can imagine that if you are using this application, there probably will be some doping, so there could be some extra electron nearby, and hence the exciton, actually the tightly bound exciton, can be just treated as a one-point particle and as an impurity to interacting with them. So initially, the spectrum, what they find is the main feature of those spectrum is that you will find that there will be the exciton's energy will shift a little bit, and then there will also be another peak showing up, which they call it a trion. So basically, this exciton is binding with another electron. But nowadays, people more and more realize that probably the many properties of the whole Fermi is actually important. So a better picture would be actually a Polaroid picture. Another important technique, the last two talk has been mentioned, is the two-dimensional spectrum. Basically, this is a one-dimensional spectrum. Basically, the signal is as a function of one frequency. However, if you explain it two frequency, I will talk about how in a second. But basically, you will see that there's already a lot of more features showing up here. One important thing is that the width or the broadening. The broadening along the diagonal term basically depends on your samples, the different maybe disorders, maybe some other effects, fluctuations. But however, on the off-diagonal term, this broadening is more generic. And then also you can see that the interesting off-diagonal peaks here in these two yellow stars showing that the couplings between these two states. So, all right then. So let me talk about a little bit more about the two-dimensional spectroscopy. In a 1D spectroscopy, basically you can use absorption of photoilluminance from a theoretical point of view. This is a linear response, or the spectroscopy of chi1. Basically, you perturb your system a little bit and see what happens, or you say that you mess around and find out. But however, what do we want if we want to know more about those characters? For example, the chi3, the nonlinear response. Well, nobody say that you can only mess up once, right? So you basically do multiple times, and you do a Fourier transform, and then you get this spectrum. And especially, for example, here, if you do this 3 time pulses, and then you Fourier transform T1 and T3, and then you get this omega 1 and omega 3 as your frequency. The reason of frequency, of course, because we like to know the energies, and energy is related to the frequency. And this is done by Jack here, and also by David's group, and also a lot of researchers from Philly. Jack just gave a very nice poster there too a couple of days ago. Yesterday. All right. So, and then, well, okay, the TMD, as you already heard Jeff's talk, it's a 2D material. So then why do we want to study 1D? Why do we want to study 1D material? One of the motivations is that because there's so-called local strain engineering. So basically, you put a nanoline on the surface and then put your 2D material on top of it, and then because the strain, then you will get some local potential. And initially, that's used to study like fusion, like how the electron would go into it. And but nowadays, in the recent research, they also study the diffusion of the extons in this channel, and also the maybe the transportation in the future. But I need to admit that nowadays the technology can only allow you to have this kind of 1D potential up to like a 1,000 nanometer. So not quite 1D, it's quasi 1D. But the people are looking forward to push it to 60 nanometer, which will become a real 1D system. Another interesting motivation for us is that we had already hear about in Dave's talk, Jeff's talk, that there are some, they are focusing on the interaction. But to study the interaction, you actually need to study the bipolar state, which theoretically is not that easy. Go to a 1D system allows us to do things in their theory. They do have a very nice theory, but that's effective theory. And we want to do a theory that with microscopy from a microscopic origin. However, to do that, we need to make our calculation workable, practical. We have to go to 1D system so that the Hamiltonian is smaller. Okay. This is a theory talk, so let me talk about my theory model. So this is hopefully this is a simple Hamiltonian. The first two terms are just kinetic energy, and then they have contact interaction. We're basically building our model on the tie binding model, so they're just hopping on this lattice side, and then the impurity and my background fermions can have different tunneling rates, so which related to their mass, and then there are also contact interactions. Even though this is just 1D, and even though there's not much electrons here, but however, the Hamiltonian can still be huge. So we actually need to use some answer to make our calculation doable. So what we use is actually called the generalized Jarvis answer. Basically, assuming that your impurity has no interaction with your Fermi C, then they're just dead. That's just one state, very simple. But however, when it really has interaction, the first state we can include is that it's just exciting one electron hole, and that's what the basis of Chevy answer. And to study the bipolar state or double polar state, we also have this kind of only including the one particle hole excitation. The one particle hole excitation for single polar actually has been tested in numerical cases, and it actually gives a very good result. So this is for the result for single polar run. If we have just one single polar run, and that's basically one of the important information is what we call residue. It's basically saying that, well, if we have the polar state and we project it back to a non-interacting state, what would be the projection of probability? And there's the base of the blue dot here, and then you can see that if there's a large blue dot there, it's corresponding to a 1D spectrum's peak. And this is just a convergent test. We're using different dimensions and of the lattice. All right. Like I said before, the trivial answer has been tested with the single polar cases, but for double polar cases, we actually haven't really tested. So that's why we first need to see whether the calculation is good. So we actually compare for this 1D case, there's actually an analytical result which is called beta answer, and this is a comparison. You can see that we have a good comparison. But naturally, you will ask a question like, well, okay, you have an analytical solution. Why do we still need to do a numerical calculation? The reason is because beta answer can only give you very good ground state energy and probably a few excited energy state, excited energy, but not the wave function and not highly highly excited state. However, our Chevy answer can give those, and you can see that this is basically this bipolar state here. Another thing you can see that, oh, okay, the bipolar state is actually it's actually smaller than the two free polar state, which means that the interaction is actually negative. But we just heard from David's talk that the interaction should be repulsive. The reason is because actually, if we also see that kind of like projection to the non-interacting state, this bipolar state or actually give a very relative small projection. The real strong repulsion actually comes here to this this we call P2 state, the double polar state. This one actually have a much larger projection. And now we have, since we already solved the Hamiltonian, we diagonalize it, we have all the eigenstates and eigenvalues, we can calculate spectrum. the process is actually quite tedious, but fortunately we have this kind of like double Feynman diagram. And once you know how to study the diagram, you can know easily to calculate those. So basically there are three important pathways. One is called the ESE, GSB, and also ESA. So that's all the very tedious formula, but the important thing is that one wants to point out is that there's a sum rule that the summation of them is just 0. And then, well, if the interaction is weak, here is the result again, like indeed. So basically the ESE and GSB just give you the peak at for example, the polaron peak. However, the ESA one actually give you a negative contribution in this one at this position. And if the double polaron state is just equal to be 2 times of the polaron energy state, they basically cancel each other. So give very small contribution. This is meaningful because if you have very weak interaction in your system, then there's not much nonlinearity. So, however, if there is a strong interaction, for example, here there is also a strong interaction because of the strong interaction induced by the Fermi C, then we can see that these two peaks actually deviate from each other, and then from the difference between them can give you the information of the repulsive interaction. We can also study the time domain oscillation. Those oscillations actually give you the energy differences between the repulsive and attractive polaron. So I come to the conclusion. So basically, we gave a microscopic theory of this kind of rephasing to these coherent spectroscopy of this 1D system in TMD materials. Of course, this is only a theory, so I would like to highlight that this kind of spectrum can tell you the interaction between the exciton polarons. And in the future, we would like to extension it to 2D materials, like what Jeff has done, and with 2 Fermi C, for example. And also another application is that I come from an ultra-cold atomic background, so we actually see that there's one way to do it in the ultra-cold gases, which is actually very similar to the NMR process. With that, I would like to thank you for staying so long. And this is our group. We're in charge here, and I'm here. So thank you.
Thank you, Jia. Great work. Questions? Got a couple of minutes for questions, comments. Jeff, yeah.
Thanks, Joe. Nice to
Thanks.
So when you talk about an attractive interaction between the polarons, I guess, do you think about that as, I guess it's the 2 polarons, or is that distinct from if you had, say, a biexciton being dressed by the Fermi C?
Yeah, I think it's mostly. I think it's mostly just a bipolaron. So what I'm thinking is that a simple picture is that you have 2 impurities and have a lot of Fermi Cs. The fermions are exchanging between them. So if you go through the second order perturbative series, there basically should be an attractive interaction. Basically, like a virtual phonon can give you Coulomb force, and or Lorentz force. That is that kind of force. But however, they are strong enough that to just bind them together and becomes basically a bound state. And you have bound state in your spectrum. Then actually in the scattering spectrum, you actually give a effective repulsive interaction. At least that would be my picture of it. Yeah.
Any other questions? Oh yeah, let's go.
So another question: in going from 1D to 2D, how different would you expect things to be?
Yeah. Well, that's a good question. Yeah, from 1D to 2D, I think we have already done it. Some similar calculation, not exactly this, but some other similar calculation. I think we can go to a 20 by 20 lattice with probably 10 or 20 electrons. That has already been done for single polaron. For double polaron, that probably is still doable, but probably we need to push it into the supercomputer instead of the MacBook just in my bag. The other thing is that you actually have 2 Fermi C. That's really what worries me, that I'm not quite sure that whether that is doable. Then maybe we have to shrink the lattice, then the finite size effect will come in, and the spectrum will probably be very broadened, and yeah.
All right. Oh, just one more.
Oh, one more.
So just to clarify for me quickly, are you saying in in 1D there seems there's an analytical solution, but in 2D you have to do it numerically, so you can't just keep going to 2D. Is that?
That's correct, but also 1D you have analytical solution for this kind of Hamiltonian, but only for calculating the ground state energy and probably a few excited state energy. But to calculate spectrum, you need all the excited state, the first thing. The second thing is that you also need the wave function to calculate the spectrum. And the analytical solution, the beta answer cannot give you. And in 2D or higher dimension, there's no analytical solution at all.
Sure.
Yeah, cool.
All right, let's thank Jia one more time.